in section 1, we looked at exponential growth. In this section, we're looking at exponential decay. So a similar pattern, but a little bit different. Rather than something growing, we're going to look at populations of things that might decay. So exponential decay is a pattern where something starts out by decreasing very, very quickly and then slowing down how fast it is decreasing. So the larger a population is, the faster it decreases, and then that rate slows down. Some things that maybe follow a pattern of exponential decay could be the value of a car. They say when you buy a car, when you drive it off the lot, it loses half of its value. That's a lot of loss very quickly, right? So it starts out with some value, it loses it very quickly, but over time, your car is going to start losing value at a slower rate and kind of start to level off and be constantly worth something, but it's not going to be decreasing so quickly. It can't decrease at that same rate because, say it was a $10,000 car, drive it off the lot, it's worth $5,000 less, and then the next day it can't be worth $5,000 less because then you'd be saying it's worth zero, but that's not the case. So it decreases very quickly and then kind of levels off, slows down how quickly it's decreasing. If you take Tylenol or something else that distributes into your bloodstream, you have your liver or kidney, something in your body takes care of that, and it goes away over time. So you take some Tylenol, and you have this large amount in there right away, and that gets taken care of pretty quickly. And then over time, it doesn't get rid of it as fast. It takes care of a large chunk of it right away, but then is only taking care of a portion of how much is in there at a time. It can only go so fast. Another example, maybe you've talked about carbon dating in one of your science classes. Carbon dating, the way that works is they look for, I think, radioactive carbon isotopes in certain elements or things like that, or in a fossil. The way that radioactive element decays, you might have heard the phrase a half-life. A certain isotope might have a half-life of 1,000 years. So let's say you have 100 grams of this radioactive carbon isotope, and its half-life is 1,000 years. Then 1,000 years later, half of that is no longer going to be radioactive. So if you start out with, what did I say, 100 grams, then 1,000 years later you'd only have 50 grams radioactive. 1,000 years later you'd be down to 25. 1,000 years later you'd be down to 12.5. So it decreases by less, the less amount that there is. The equation that we'll see for exponential decay is going to look very similar to exponential growth, but just with one minor change. A number that we multiply in front still has to be positive, so we still have to have a positive function there. But the base of our exponent is going to be between 0 and 1. So the base of that exponent might be a half, it might be 1/3, it might be 2/3, but something that's between 0 and 1, because as we multiply by that fraction, it's going to get smaller and smaller the more times we multiply by it. So just a real basic example would be y equals 1/2 to the x. Every time we multiply by 1/2, that's going to get smaller. It's going to be 1/2, then 1/4, then 1/16, or sorry, 1/8, 1/16, 1/32, right? So it's going to start out larger and get smaller and smaller as x goes up. One other difference, we could rewrite y equals 1/2 to the x. This would be the same as y equals 2 to the negative x. So if we see a base that's greater than 1, but with a negative exponent, again, that's really the same as flipping that 2 over and making it a 1/2 to the positive x. Okay, so if we see a number greater than 1 but with a negative exponent, that is decay. So again, one of the key things that I want you to be able to do this chapter is look at an equation or a graph and tell me whether it's exponential growth or decay. So that's one of the little things that you'll need to look for as you determine some of those. I would think looking at a graph, you should be able to pretty easily tell the difference between exponential growth and decay. So let's look at these examples where all we have is the equation. Determine if it's exponential growth or decay. So in the first one, that 1/2 doesn't really matter. That's kind of just our starting value. That would maybe be the principal in one of those compound interest problems. All that matters is that's positive. Being 1/2 doesn't change whether it's growth or decay. So here we have a base of 3. That's something greater than 1. Every time that we multiply by that 3 again, it's going to get larger. That 3 is greater than 1. This is exponential growth. And the next one, again, that 2 doesn't matter. It just has to be positive, and it is. That 2/5, that's between 0 and 1. So every time that we multiply by 2/5 again, that value is going to get smaller. So the value is shrinking. So this is exponential decay. Here, 3 times 1/2 to the x. Same as the one before, that's between 0 and 1. So this one would be decay. Every time we multiply by that 1/2, we'd be getting smaller. And last one, trying to trick you a little bit, 1/4, so that's smaller than 1, but it's to the negative exponent. So this would be the same, we could flip that over, and this would be the same as 4 to the positive x. So there we have an exponent larger than 1. Every time we multiply by 4, we're getting larger, so this is exponential growth.